Hi, welcome back to my videos. In the previous videos I have shown a presentation on the simulation of single phase AC phase voltage controller using Proteus and Arduino as a digital controller, and I have applied that on dimmer circuit. And also in another videos I have shown a real experimentation on the application of such circuit on a dimmer circuit as well as on a universal motor so that we can control the light intensity of the light bulb and also the motor speed accordingly. Now in this video I will show another technique that is also used as an AC to AC converter without changing the frequency of the supply voltage. This technique is called the integral cycle control, as well as in some cases it is called cycle stealing or pulse stealing, or eventually it is called burst firing or burst fire. The idea behind such technique that you choose a control period. For example, we choose in this case we will choose 5 cycles, and what we will do, we will eliminate 1 out of 5 or 2 out of 5 complete cycles or 3 complete cycles out of 5, etc., etc. By doing so, what we will achieve that we will minimize or lower the RMS voltage across the load. Hence, in that case, we will get a lower light intensity or lower motor speed. So the difference between the two techniques, and the first one that's called the phase voltage control, what we did, we have removed part of the signal, the incoming signal or the incoming voltage that's coming across the thyristors or triac, and eventually goes to the load, and we have removed part of that voltage according to what is called the firing angle that comes from the Arduino. So by doing so, we have minimized or lowered the RMS voltage across the load. But in this case, what we will do, either we will remove the complete cycle, 1 complete cycle, or 2 complete cycles, or 3, 5, or 4, or 5, etc., based on the code that we have written in Arduino, or so that we can actually control the RMS value. So the advantage of using that technique actually, which is called the integral cycle control, over the previous one, that you end up having no harmonics in the line voltages or the phase voltages, because simply we don't distort the incoming signal. We have a complete cycle or we don't have it. So that's the idea behind it. Whereas in the previous technique, which is called the phase voltage control, it has many harmonics inside the output voltage, and the harmonics actually is proportional to the firing angle, and the more you increase the potentiometer here, the voltage, the resistance that you can control, then in that case you will end up increasing the firing angle, and in that case the RMS voltage, of course, will be getting less and less, but the harmonic distortion will be higher. In this technique, we will use these 2 buttons. For example, this button will be used to increase the cycles across the control period, whereas this button we will use it to lower the cycles across over the control period. This button is we can use it for the maximum speed. So eventually we will have the full period, the full cycles across the control period. So that in that case you will get the highest and the maximum RMS voltage across the load. Again, we have used, in this case, we have used a power supply that is 220 volt RMS, and the frequency will be 50 hertz. The circuit is almost similar to the circuit that I have used in the previous one, which is the phase voltage control. We have a step down transformer, and we have a full bridge rectifier that is feeding the optocoupler, which will work as a zero crossing detector, and the output from the optocoupler will be sent to the external interrupt pin number 2 of Arduino, and then we will be able to generate a pulse that will goes to the optotrack. We will have it from pin number 5 and across the optotrack, which will feed the track, and eventually we will be able to control the RMS voltage across the load. Again, as I said, the difference here, we have added 3 buttons to control the number of cycles that will be passed through the track, so that we can control the voltage, the RMS voltage across the load. So basically the hardware is the same. There's not much difference in the hardware. Actually, the code, the secret is behind the code. What I have done, I have added a few lines. As you can see here in the void loops, I have added some lines to indicate the control of the buttons, and I have added some registers so that as a counters to count the pulses, the number of pulses, and in the ISR, in the interrupt service routine as well, that's going to be called across the attach interrupt. The AC on function, that it will do again the required perform analysis in order to calculate the required number of pulses to pass through the optotrack and eventually to the optotrack, and by pressing the button, then it will decide which number of pulses and how many pulses that should go to the optotrack to work the tracks and to get the required RMS voltage. I think we will go now to run the simulation. It's better now to run it and see the output result on the oscilloscope. Okay, let's see how it is gonna go. Alright, we will skip that oscilloscope because that's gonna show the input power supplies, and we will focus on that one, actually, that oscilloscope. And as you can see here, this is the screen that shows the frequency of the supply, that's 50 hertz. And what we see here is the pulses that is coming from the optocoupler. So I'll increase the scale over here. So this is the pulse that comes into external pins from the optocoupler and goes to from the optocoupler to the external pins of Arduino pin number 2. And if I press on that button, for example, what we will see the pulse. We will see the pulse across the load, which is 1 cycle. Eventually, yes, that's it. So you see the 2 blue pulses here. That is corresponding to the pulses going out from pin number 5 from the Arduino. So when I press one button, the Arduino code will calculate how many pulses that I must send to the optotrack and eventually to the track, so that 1 cycle will be out from that control. So you can see the output voltage here is varying slightly, but averaging we will talk about 100 RMS value, and the light intensity is a little bit low. Now let's switch the button once again. So we have 2 pulses at least now. Okay, so if you go and see now, you will see that 2 cycles. That on auto, yes. So you see that is 2 cycles out of 5 Yes. So if we increase, and we will see the light intensity has increased, the RMS voltage also has increased up to 130 as an average, and also I will press that button again, so we'll calculate 3 pulses or 3 cycles out of 5. That's corresponding to a 60% of the full scale. Yes, so that's now we are having as 3 cycles out of 5. And you can see again the light intensity has increased, and the RMS voltage also has increased accordingly. We'll keep continuing pressing the button. This is going to be the 4th time, which means that this is going to be 4 cycles out of 5, which is corresponding to 80% of the full scale. Now, as you can see here, the light intensity has increased, the RMS value. Now let's have the full scale actually, which is 5 out of 5, and see what's going to go on. Yes, so as you can see here, we have the full scale. Actually, the light has gone into the maximum illumination, and the RMS value is which is equal to the power supply or the input value of the RMS voltage. That's 217, 200 and something like that. So that's the idea behind it. And as you can see here, in this case, we have a complete AC sinusoidal signal that's coming across the load. So there is no harmonics across the load, because either we have the complete cycle on or the complete cycle off. And that's the idea behind the this technique. Now what I will do also, I will show you also, we have done in this kind of technique that also we can have the capability of having a hybrid solution. Actually, you can mix the 2 techniques together. So we still have a phase voltage control, like if you see here, now I'm changing the potentiometer value, so that eventually it will change the phase angle or the firing angle across the voltage across the load. And as you can see here, we still have the both technique applied to the same circuit. I can again minimize the number of cycles. So here again we are losing 1 cycle, and also if I can press the button again, then we will have 2 pulses out, and then the remaining will be 3 complete cycles. I can also make it 2 pulses in and 3 out. I can make it 1 pulse in and 4 out, and I can switch it off. There is no pulses coming out, and again I can switch 1 pulse and also go back, and I have the complete cycle. I can also increase the firing angle, so we will have, yes, so you can see that the voltage waveform is changing according to the firing angle. Yes, we can also go back and increase it, get it back to the full sinusoidal waveform. Yes, like this. So we will have 0 firing angle, and we will have a full wave sinusoidal waveform. What you can do also, you can switch that button on, so which will give you the maximum speed or the maximum light intensity, like this. So you can see the RMS value has increased, so the illumination has increased. Well, and that is simulation wise. What I have done a real experimentation on that technique, and I will, in the next videos I will show you this kind of technique applied on a light bulb and also applied on a universal motor, and we'll come back to you and we will discuss it again. But I will let you I will give you a brief that one of the disadvantages of this technique that you are gonna see while we were working on the light bulb or in the motor, that you will see a flickering in the bulb, because now what we will do, you will see 1 complete cycle is disappeared, or two complete cycles is disappeared. This will show that kind of flickering on the light bulb, and also we will end up having a pulsating torque on the motor. But again, you can minimize this by increasing the number of cycles in the control period. For example, in this case, we have used the percentage of control is 20%. The minimum percentage scale is 20%, which is 1/5. Whereas if you increase the number of complete cycles or the control period, make it 10, for example. So if you eliminate one cycle, it's going to be 1/10, which is 10%. So if you make it 20 cycles, if you make the period, the control periods 20 cycles, so 1/20 will be 0.05 and etc. etc. So it depends on how precise you want to control your devices or your system, and then you can eventually make it more precise by increasing the cycles over the control period. We'll come back and discuss it in details once we get the experimental side, the videos again. Thank you very much for listening. See you again.